Hello everybody, my name is Barsha and we are talking about matrix multiplication using 2D array of threads inside 2D array of blocks. This is our example for this time. So in previous case we have threads which are deployed inside the one block, but in this case we have multiple threads, but they are scheduled to the different block of threads. So it's good to have this theoretical explanation before we do the program. So we have still we have matrix multiplication problem, and we are solving it with the threads on the GPU and device as a device. And first of all, for result matrix, we are forming for each element we are forming the thread which is calculating that element of the matrix C. So that's the name of the game. That is what we are doing. And in this case, we are not using one block of threads, but we are putting multiple blocks in the game, and we also scheduling multiple threads inside of them. So, and what is also important to be said that beside the situation that we have thread IDX indexes and thread IDX epsilon indexes, we have also blocks and block indexes which will be used in this case. But how we are doing it, we will see later. Of course, still each block is executed on one streaming multiprocessor. And why is this important? In case that we have, let's say, large scale matrices which we are multiplying, we need to separate these group of threads inside the blocks and do the, let's say, spread them to be executed on resources that we have in our let's say in our capacity. So especially so this kind of solution for the problem when we are making multiple blocks, and in this case 2D array of blocks, it's important when we have large scale matrices, and then we want to maximize usage of our resources, our GPU resources, which means how to equally load our streaming multiprocessor inside the GPU. So we are creating blocks, and one thing which is called, I think, scheduler or something like that, we will explain that in the hardware, is doing this job of taking care of scheduling of the threads and blocks and stuff like that. So threads which are corresponding to the solution of the each element of the matrix C, to them are assigned some threads, and they are also deployed inside the blocks. Threads and blocks are going X and epsilon direction, and this is equaling in each block. As you can see, we have scheduled equal number of threads, and we putting all that blocks to be executed on different streaming multiprocessor to not wait too much and go with one block on, because one streaming multiprocessor is always executing one block of threads. So that's the issue that we are solving here, and the kind of approach that we are doing, 2D array of threads inside 2D array of blocks. Both of them are obviously 2D array in form of 2D array of array. So in this case, threads are distributed in the multiple blocks, and one block is executed only on one streaming multiprocessor on GPU. So we can go further with this. The problem is similar, but this time we have blocks dedicated to each section of the matrix C, but still using the same principle. We are picking up the row of matrix A and column of matrix B, and multiply corresponding elements, adding that multiplication, and we forming the elements, and one thread is taking care of one of that element of the matrix C. So for all 8 times 8 64 elements in the result matrix C, we are forming the threads, which are grouped in 2D array of blocks. So multiple threads, 2D array of threads are grouped in blocks, and we have 2D array of blocks. So in this case, we have 2 times 2, 4 blocks in this example. So 2 blocks in x direction, 2 blocks in epsilon direction. So 2 times 2 is equal 4 blocks for solution of this problem. Also, for all 8 times 8 64 elements in result matrix C, we are forming threads which are calculating those elements of matrix C by multiplying and adding respective elements of row of matrix A and column of matrix B. What does it mean? This is standard way how we forming one element, and we use one thread to execute this thing what is said here. And we have entry matrix A and entry matrix B. Both of them are 68 times 8 with the 64 elements, and result matrix is C, and element of the C is formed on standard way. Beside of that, one thread is taking care of that multiplication and adding, and we use indexing and parallelization in sense of easier and faster solving of this issue and maximizing the resources for the parallelization of these processes. So yes, we are forming threads, we are forming 2D array of threads, but each 2D array of threads is inside of one block, and also there is 2D array of that kind of blocks. So I think everybody understands what is the name of the game. So dimensionality of each block for this case is given here. So block dimension dot x for each is same for each block. So 4 times 4 as you can see. So each block have a 4 times 4, it's 16 threads in each block. And then of course when we call the kernel function multiple times, we use corresponding thread index and block index for finding the coordinates of each thread, and using that indexes properly for the finding the solution for that element. So I hope we understood what is happening here, and these pictures can help you to imagine what is happening. But one thread is executing and calculating one element of the matrix C by picking up row and column from the matrix B. Then we want to find a way to explain logically these indexes that we are putting here now. Of course, we have for threads inside the block, we use thread ID x and thread ID epsilon. So inside of each block, we have that same from the start, same indexes, which will be seen here. So, and also we have indexes for the blocks, which are visible here. So what is important to know here? We have x-axis, and we are counting the thread IDX inside the one block by this thread ID indexes, but we also counting the blocks in x direction with this built-in variable in x direction. Also same and similar in the epsilon direction inside each and every one of the blocks. We have thread ID x indexes, which is going the same way as you can see here, from 0 to 3 to pick up all inside of the blocks, inside of this block. And also the next one, let's say in epsilon direction, we are going the same counting as you can see here. So but with the increase with number of blocks here, so we can do the proper addressing and indexing of this element, which we are calculating through the threads which are executing these functions. Also, in X direction, you see that we are picking up all thread IDX indexes .x 0, 1, 2, 3, and also in next block, but with the increase of block index 1, also we are picking the same way thread IDX from 0 to from 0 to 3, and this is dimensionality of the block in X direction, and this is dimensionality of block in epsilon direction, and this could help us to jump from address to address and help indexing. So we need to, so we can know which element we are calculating and what are we doing. So I hope that you understand that block IDX and thread IDX are combined together to form index of each thread. So if we want to pick up, for example, this thread, we need to combine this block IDX.x index, this block IDX.epsilon index to locate the block, and then inside the block we are using thread IDX.x and thread IDX.epsilon to locate inside of that block specific thread that we want to calculate for some element. And I hope this is all clear what is happening and how to do proper indexing for blocks and threads, and how to pick up a specific thread with the help of these built-in variables. So let's go further. This is more, let's say, this is similar, but let's say more obvious with the specific and the exact exact values of thread IDX.x and thread IDX.epsilon inside of each block, all for all specific threads. These block IDX and thread IDX.epsilon and .x are unique for each thread, which are forming out of the kernel. So you can see that we are, for this block IDX.x and block IDX.epsilon, these are coordinates of this block, and inside of it we have all these 3, 1, 0, 1, 2, 3, 0, 1, 2, 3, thread IDX.x and thread IDX.epsilon values, which are helping to pick up a specific thread index inside that specific block. Then if we want to jump to the next block, we also have exact block IDX.epsilon coordinates for that block, and also on the X axis. And then inside of that block we are searching for the specific thread inside of the block with the help of thread IDX.x and the thread IDX.epsilon, which is picking up again same values as here, but in another block, and that helps us to calculate with the arithmetic specific address of the element inside of memory, where to put some value which we gain in calculation of the matrix multiplication of row and column of elements of matrices A and B. And these threads are calculating element with the help of these rows and columns multiplication element of the matrix C. So for picking up the specific row and column index, also for the matrices A and B, where we're picking up rows and columns, this corresponding to the specific thread ID index thread index, which is corresponding to the result matrix. And with the definition here, which is given in the body of the kernel function, this help us to pick up a specific thread index, which we are calculating, or element which we are calculating, and then with that index also we picking up specific row of the column, specific row of matrix A and specific column of the matrix B to calculate that to that element. And also what is need to be said, that 64 elements of the result matrix C, which we need to be calculated. In this case, we have 2 times 2 blocks with 4 times 4 in each block, 4 times 4 threads, which is visible here, which is 16 threads inside the one block, which is in total 4 blocks times 16 threads, which gives 64 threads. And this can help us to pick up this let's say this here is helping us to pick up all these rows and columns, also for the threads, but also for the rows and columns of the matrix A and matrix B. What is happening here? How we're searching these coordinates? Like we know through the we're picking up specific block for the row. So this block index or this block index, and then when we inside of that block index we have times dimensionality, because to jumping over all this when you pick up, let's say 1, you jumping over all these in block 1. 0, block 0, you are jumping over all these addresses, and then you, with a specific thread idx.epsilon, you picking up specific row where you put your element, and also row where you picking up the elements of the matrix B. No, rows, we are picking up specific row, the elements with the elements of the matrix A. But columns, it's the same. If we want to pick up a specific column, where is that thread? Let's say here, you need to use this block idx.x index to pick specific block. Where is that element? And also you need to use that for that address you need to, let's say, blockdime.x, which is helping you to do what? Let's see. Yes. Yeah. You're picking a specific we are picking up specific block. Yeah, when you and also you're skipping all this if this is the block we want. Let's say this element which have block idx.x equals 1, so we are putting that value here, or automatically it is put here, and we are multiplying with here, pardon, but we're multiplying with dimensionality, so to skip all these addresses to go and find this specific column or block. This is helping us to define this beginning and specific block, and then with this specific value of thread idx.x, we are picking up a specific column in that case. The job is similar previously, so dimensionality here is helping us to jumping over the addresses we don't want and go to specific address where column starts and so on. This index is used to picking up all elements. This defined value here is helping you to picking up all the column elements from the entry matrix B. because from the matrix B we are picking up columns, and from the matrix A we are picking up the rows. But these are also indexes of that specific thread. How do we define multi-dimensionality of our threads and indexes? We define it with the dim3. So threads per block is 4 times 4, dimensionality of the block, and number of blocks in grid 2 times 2, as you can see. 1, 2, 2 in epsilon direction, 2 in x direction, so it will be in total 4. And also threads per block is going here in calling of the kernel function, which help us to turn this kernel into multiple threads. And number of blocks, it's 2 times 2, 2 in x direction, and 2 in epsilon dimension. So these values are put it here, and this goes number of blocks inside of the grid. Also, it's 2D array of blocks, and this is 2D array of threads. So these values are for here. And we are putting here entry matrix A and B, from which we will take rows and columns, multiply them, and store it in the matrix C. So the job and the name of the game is the similar, and this is given inside the body. We have specific row and specific column. We explain how we gain them, and we need to pick up all these elements from the row of the matrix A and the column of the matrix B, and there is specific arithmetic which is doing that. We are walking through the row and column in the same way, because the number of elements in row and column must be equal for this matrix multiplication. So this is walking through, but these row index and column index are formed now with the help also not just the thread idx.x, but also with the help of blocks, which blocks and threads uniquely helping us to picking up and find the coordinates for the specific row and column, and for specific element. And if we are inside of that element, which we have coordinates, also we're picking up the row of the corresponding matrix A and column of the B or corresponding matrix B, which are multiplying here. This process we explained multiple times. We multiplying each corresponding elements, and then add them to the sum. We start from the 0, and then every each and new multiplication we are adding on that sum, and we are literally picking up all these elements to multiply and add them to the sum. And when the k is run over, or when we go through this sequence with the for loop, and we count all the k's, the total number in sum is actually the formed element of the matrix C, also with a specific coordinate, which is logical according to the row, because also the row is calculated in that way that taking in account also block idx index and thread idx dot epsilon. Everything here is epsilon. And to store that element C, the rule of multiplication of and forming the resulting element is given here. And for each thread formed out of the kernel function, we have fixed indexes for y and x. And we, for each element, we use all these 4 elements in rows and columns definition to pick up that specific element and pick up that specific row and pick up that specific column from the entry matrices A and B. So we can go through this. And what is this doing? It is literally address arithmetic. This is starting addresses, and we are, with this help of this address arithmetic, we are jumping over the addresses and go to the specific address of the element which is inside the row, to pick it up and multiply it with the corresponding element inside here with the help of this address arithmetic, jumping over all other elements. Let's say this is the element, we are jumping all over these elements in the columns or their addresses to pick up that specific address and do the multiplication of element of A and element of column B. And this K is helping us to walk through all these elements in row and column. This was explained multiple times, so I don't want to waste too much time here. And let's see in the final stage what is kernel function doing actually, and to combine all these things and words that we said. Also, just one notice that when we have result here of the multiplication and adding, we put it up and we are using it in the next sequence. That's why it's sum up here when we're going through the for loop for each value. In every sequence of the loop, we are picking up all that old value and adding up to the multiplicate of these 2 elements and using in the next sequence. So that's, I hope, obvious. All same like we talked before, but just using a block and the block indexes and block dimension to help us find the specific threads. And when we put if we don't want, what is the purpose of this? Let's say if we don't want to have 2 large blocks, a block with too many threads, and one thread is always executed on one streaming multiprocessor, and we want to use more resources and in parallel as much as possible, we spread and make multiple blocks and put that blocks on the multiple streaming multiprocessors, not just one streaming multiprocessor, and put that thing into calculation and do it in parallel way to avoid too much waste of time and waiting on the execution of the program, and fastness through the parallelization is the main task here. So that's why we learning all this may be confusing stuff, but the point is why we are making blocks. We are making blocks to make multiple blocks, because multiple blocks can be executed on multiple streaming multiprocessor. But if we make one large block, it's always executed on the one streaming multiprocessor. So that's why we're making multiple blocks, to increase the performance of our parallelization. So configuration here is 2 times 2 blocks, and each block is 4 times 4 threads. This is section just for the calling in main program. We defined threads per block, that we are using 2D array of threads inside one block, and that we are using multiple blocks inside of the grid. So we have 2 times 2 blocks or 2D array of blocks to increase the parallelization and doing that stuff on the multiple streaming multiprocessor. So we want to separate these blocks and put them, each of them, as much as possible on a different streaming multiprocessor, which is part of the GPU, which are part of the many of them of the GPU, and increase the performance and use parallelization to play game for us. So kernel for matrix multiplication. This was kernel. This is a defined kernel which will be turned into multiple. By the way of calling here, this will be turned into multiple threads inside of the multiple blocks, and all of that 2D. Of course, global, which means we are calling from the host and execute on the device. Void, of course, and the name of the function. Just want to say that we are doing the business of the matrix multiplication kernel, and we are forming multiple threads which are spread into the blocks out of this kernel function, and we giving up the pointers to the A and the B. A and the B of the entry matrices, but they must be, of course, located inside these locations inside the GPU or device memory, and also results are stored inside the C, which are also must be on the GPU memory if we want to use kernel function. Also, again, how we define row and column, but with the help of indexes for the blocks and dimensionality, which helping us to doing arithmetic to jump to specific thread inside the specific block, and all these thread ID indexes are going from 0 to 3 for each block, and we have different indexes for the block. Also similar, this is also for the picking up the rows. Remember, we are going through epsilon and picking up rows in epsilon direction, which can be used to identify element of the matrix C or result matrix, and also picking up specific row from the entry matrix A. Also same for the columns. We are doing indexing through the block IDX index, its dimensionality, and thread IDX, as we say and in the previous slide. So we jumping to the specific block, and then inside of that block with the dimensionality here, which help us to separate from the beginning address. Also jump inside the specific thread inside of that block, and the case is same as for the columns. And this column identifies where in which column is result element of the matrix C, and also the same index is for to be picked up in the column, or which column we are picking up from the entry matrix P. Yeah, the case is similar before. We are defining the sum and go through this sequential execution in for loop, which help us to with the index k to pick up all these elements from the rows and the columns and multiply them mutually, which we explained. And also after we finish with that for loop, we storing that sum in that specific element result of the result matrix C, which is indexed in this way, which we explained multiple times. And also starting from the matrix C, address arithmetic is helping us to identify that specific element and jump on its address and to do the demanding change of its value. So this is all for the theory, and this will help us visually to understand when we do the program what is exactly happening there, and to better understand how we use now blocks, multiple blocks, which are two, and that we have 2D array of blocks. So we have blocks in x dimension and epsilon dimension, and we want to maximize and increase the performance of our parallelization, and we are doing it through the blocks, because when we put so many elements in different blocks, it helps us to spread our tasks to multiple streaming multiprocessor, in the difference with the case where if we stayed on the one block, that one block is only can be executed on the one streaming multiprocessor, but when we separate in multiple blocks, all these blocks can be executed on the multiple streaming multiprocessor, and that is why are we doing here this thing, and why are we learning this, which may be sound confusing. Okay, it's not just that we are playing with the blocks, it has its own purpose. So that's enough for this video, and see you in a practical video which is doing this all through the CUDA C++ program, which is executing this thing that we said here in this video, theoretically. Until that, bye bye.